Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and today we're diving deeper into distributed hash tables. Before we begin, I'd like to remind our listeners to rate our podcast on your favorite platform. Your feedback helps us improve and reach more developers like you. Now let's get started with an interesting quiz question. What mathematical operation is at the heart of the Kademlia algorithm's distance calculation?
That's an intriguing question, Sheila. It's not something you'd typically associate with distributed systems, is it? I'm curious to see how many of our listeners can guess this one. It's a fundamental operation that most developers are familiar with, but its application in this context might be surprising.
Absolutely, Victor. To help our listeners understand today's topic better, could you briefly explain what a distributed hash table is and why we're discussing different algorithms for them?
Certainly. A distributed hash table, or DHT, is a decentralized system for storing and retrieving data across a network of nodes. We're exploring different algorithms because each has its own approach to efficiently organizing and locating data in this distributed environment. The Kademlia algorithm, which we're focusing on today, is one of the most popular and efficient DHT algorithms out there.
Thanks for that refresher, Victor. Now let's start with the basics. What motivated the creation of the Kademlia algorithm, and how does it differ from the chord algorithm we discussed in our previous episode?
Great question. Kademlia was created in 2002 by Petr Maymunkov and David Mazieres, with the goal of improving upon existing DHT algorithms like chord. The main motivation was to create a more efficient and fault-tolerant system for peer-to-peer networks. Unlike chord, which uses a ring topology, Kademlia uses a tree-like structure and introduces a unique distance metric that significantly improves routing efficiency.
That's interesting. You mentioned a unique distance metric. Can you elaborate on that? I believe it's related to our quiz question.
You're absolutely right, Sheila. The heart of Kademlia's efficiency lies in its use of the XOR, exclusive OR operation, to calculate the distance between nodes. This XOR metric has some fascinating properties that make it ideal for DHTs. For example, the distance between a node and itself is always 0, and the distance is symmetric, meaning the distance from A to B is the same as from B to A.
I see. So, if I understand correctly, Kademlia uses the XOR operation to determine how close nodes are to each other in the network. But how does this translate to organizing and finding data?
Excellent question. Kademlia organizes nodes and data using what's called K-buckets. Each node maintains a set of these K-buckets, which are essentially lists of other nodes in the network. The K in K-bucket refers to the maximum number of nodes that can be stored in each bucket, typically around 20.
That's fascinating. It sounds like a clever way to organize a large network. But I'm curious, how do these K-buckets relate to the XOR distance we talked about earlier?
Great point, Sheila. The K-buckets are organized based on the XOR distance from the node itself. Each K-bucket covers a specific range of distances. Nodes that are closer, in terms of XOR distance, to the current node are stored in lower index buckets, while nodes that are farther away are stored in higher index buckets. This organization allows for efficient routing and lookups in the network.
I think I'm starting to see how this all fits together. It's almost like organizing a library, isn't it? With books, or in this case nodes, being placed on different shelves based on how similar they are to a reference point.
That's an excellent analogy, Sheila. Imagine a library where each book has a unique binary code instead of a traditional call number. The librarian, our node, organizes the books on shelves, our K-buckets, based on how different their codes are from the librarian's own code. Books with very different codes go on far shelves, while books with similar codes are kept closer. This organization makes it easy for the librarian to quickly find any book, even in a massive library.
That really helps visualize the concept, Victor. Now, I'm curious about how this organization translates into actually finding data in the network. Can you walk us through the lookup process?
Certainly. When a node wants to find a piece of data, it starts by calculating the XOR distance between the data's key and its own ID. Then it looks in its K buckets for the nodes closest to the key. It sends parallel lookup requests to these nodes, which in turn do the same thing, check their K buckets, and return information about the closest nodes they know. This process continues, with each step getting closer to the target until the node holding the data is found.
That sounds incredibly efficient. It seems like you'd be able to find data very quickly, even in a huge network. Are there any real-world implementations of Kademlia that our listeners might be familiar with?
Absolutely. One of the most well-known implementations of Kademlia is in the BitTorrent network. The BitTorrent distributed hash table uses a variant of Kademlia to help peers find each other without relying on centralized trackers. It's a great example of how this algorithm can be applied to create robust, decentralized systems at scale.
That's fascinating, Victor. Now, before we wrap up, I think it's time to reveal the answer to our quiz question. The mathematical operation at the heart of Kademlia's distance calculation is indeed the XOR operation. It's amazing how such a simple operation can be the foundation for such a powerful distributed system.
Absolutely, Sheila. It's a testament to the elegance of the Kademlia design. The use of XOR for distance calculation, combined with the K-bucket system, allows for efficient routing, resilience to network churn, and natural load balancing. These features make Kademlia stand out among DHT algorithms.
Thank you, Victor, for this enlightening discussion. To summarize what we've learned today, Kademlia is a DHT algorithm that uses XOR distance and K-buckets to efficiently organize and locate data in a distributed network. Its unique design offers advantages in routing efficiency and fault tolerance, making it a popular choice for large-scale peer-to-peer systems like BitTorrent.
That's a great summary, Sheila. I hope our listeners found this deep dive into Kademlia as fascinating as we did. Remember, understanding these fundamental algorithms is crucial for anyone looking to build robust, decentralized applications.
Absolutely, Victor. And to our listeners, we'd love to hear from you. Visit crashcasts.com to join our Discord community and let us know what you thought of today's episode. If you're enjoying our content, please consider supporting us on Patreon. Your support helps us continue creating these in-depth explorations of decentralized technologies. Until next time, happy coding.